Welcome to the 2022 edition of the Federico Tonielli Award. This is an event organized in collaboration with Cole University and with l'Istituto di Scienze Umane and Esistenziali. I'm very happy to see with us this time several members of the family, Daniela, Gianfranco, and I have to say that the commitment of many students, in particular Vasco Cavina, who will moderate the Pisa part of this event, Marcello Andolina, Paolo Erdmann, and also many colleagues, shows really how the memory of Federico is still vivid in the Scuola and surely also in Cole University. Many thanks also to my colleague Sebastian Dell for the good collaboration in the organization of this event, to our colleagues, in particular to Andrea Gambassi, who will give a talk this morning, and also to the musicians who kindly accepted to contribute. So I don't use more time, and I leave immediately the floor to Vasco, who will moderate this session. Thank you.
Good morning to everybody. First of all, I want to thank Professor Ambrosio for all his support and for making this event possible. And also I would like to thank Professor Buffardi from Istituto di Scienze Umane ed Esistenziali and Professor Dill from the University of Köln. As a friend of Federico, I'm really happy to be here and to represent all the other friends and fellow students of the University of Pisa and Scuola Normale. And a lot of them are following online today, and I want to greet all of them and all the other spectators, and also Daniela that is in the audience. And we are ready to welcome our first guest. And in this first part of our workshop, we will do a small journey in which we will touch many aspects of the life of Federico. And we start with one of the things that was most relevant to him, that is music. So I would like to welcome on stage Maestro Piero Viti and Maestro Mauro Bibò, that will accompany us today with the music. And Piero and Mauro are artists of international caliber, and on behalf of all of us, I really thank them to be here. Mauro is a flutist and orchestral conductor, and Piero is a guitarist and professor at the Conservatory of Benevento. And I want also to mention that Piero was a friend of Federico, and so I guess that they talked a lot of times about the relation between physics and music. And the first piece that Mauro and Piero will play is a bit telling us about these conversations, because it's a composition of Johann Sebastian Bach, one of the fathers of modern music and a pioneer of the study of the relations between mathematics and music. And also is a way to pay a tribute to our friends that are following from Germany, because Bach is also the father of German music. And with this, I leave the ground to Maestro Viti and Maestro Bibò, that will play Sonata in Do Maggiore of Johann Sebastian Bach. thank you, Piero and Mauro, for the first of many musical contributions of today. And we were saying that we want to follow the journey of Federico today. And with the second guest, we will visit, in a certain sense, Aversa, that is the city where Federico has grown with his family. And our second guest is Professor Adriana Mincione, that is connected from the high school Enrico Fermi in Aversa, and with the help of Professor Pasquale Pagano, that will translate for us the words of Prof. Adriana Mincione. Professor Mincione is the director of School Enrico Fermi, that is the school where Federico has studied, and that has also given other students to Scuola Normale. And this is not by chance, since Liceo Enrico Fermi is an high school in which every year a particular effort is devoted to university orientation and to the valorization of excellence. Professor Mincione has some memories to share with us, and will talk about a beautiful initiative that the High School Enrico Fermi is taking to honor Federico, his spirit of belonging to Campania, and his love for science. Thank you, Professor Mincione.
Liceo Fermi, io vi dico, ho molto il piacere di conoscere Federico, ma siamo onorati che nel suo passaggio per questo liceo. E più di me potrà dire il docente che lo
We are honored to be here. I'm here to translate from Mrs. Mincione's words. And next to me, there is Mrs. Mincione, who is the director of Liceo Fermi, and Mr. Eugenio Trovato, who is Federico's former Italian teacher. We are very honored to be here today. And one thing that Ms. Mincione wants to highlight is that Federico will be remembered in July during a special ceremony that will be held here at our school. All his classmates and also his former teachers will be invited to the ceremony. Now, let me leave the floor to Mr. Eugenio Trovato, who is Federico's former Italian teacher, and he will address his greetings to you, and I will be translating for you.
Sostenere di aver conosciuto, di aver avuto il privilegio di conoscere Federico non è un'affermazione retorica. Chi si accostava a lui aveva l'immediata sensazione di trovarsi di fronte ad una rara forma di sensibilità e di intelligenza, un'intelligenza fuori da ogni schema, un'intelligenza molto particolare.
It's of course not pure rhetoric to say that we are all very pleased to have known Federico. Every person who met him had this idea of meeting a rare form of sensitivity.
Di lui ricordiamo la sua capacità di essere così profondo, ma nello stesso tempo anche così leggero, di poter discutere di qualsiasi argomento con una profondità eccezionale, ma nello stesso tempo saper scendere a terra e relazionarsi ai suoi compagni in modo normale, anche di argomenti leggeri, frivoli.
Of course, what we remember of him is the fact that he was at the same time very deep in his thoughts and in his reflections, and at the same time very light and friendly to his classmates.
Il suo ricordo è ancora vivo e ci auguriamo che possa continuare a brillare, a illuminare le nostre strade, perché sicuramente la sua meteora ci ha lasciato, diciamo, questa tristezza sulla precarietà del destino umano, ma anche la speranza e la fiducia che, come dire, possiamo continuare ad attingere le vette più alte della conoscenza.
Although his presence here was very short, we really believe and want to remember him, and we really want his presence and his memory to highlight the presence of all the students who will be in this school in the next years. Thank you, everybody.
thank you very much to all the people connected from Liceo Fermi and for this beautiful initiative to honor Federico. Now it's time to welcome again Piero Viti and Mauro Bibbò for another musical piece. This time they have chosen for us a composition of Heitor Villa-Lobos. Villa-Lobos was a Brazilian composer, one of the most important musicians of the last century. And he was famous, among the other things, for his reinterpretation of Johann Sebastian Bach in a more Latin and Southern key. In this piece there is then a bit of Germany, a bit of the Latin world, and also, thanks to Piero and Mauro, a bit of the city of Naples and a bit of our friend Federico. So I leave again the stage to Piero Viti and Mauro Bibbò with Bachiana Brasileiras number 5. Thank you again, Piero and Mauro. Now we want to talk about the passion of Federico for physics. This passion is the reason why we are here in this room to celebrate this day. In fact, the love for science is what led Federico here in Scuola Normale in 2010, where he became a reference point for all the community of the school. There are also some professors that Federico had in Scuola Normale when he was here that are following us. For instance, there is Professor La Rocca here in presence. And after becoming a reference point for all the people in the Scuola Normale, and after graduating in 2016, Federico started a PhD in Köln with Professor Dill, and this research was focused in non-equilibrium physics and statistical mechanics. This last is the main topic of the talk of our third guest, Professor Andrea Gambassi of SISSA, that I welcome. SISSA, Scuola Internazionale Superiore di Studi Avanzati, International Superior School of Advanced Studies, in Trieste, is one of the most prestigious research institutions in physics in the world, and Professor Gambassi's research spans from the already mentioned statistical mechanics and non-equilibrium physics to stochastic processes and critical phenomena. With more than 70 publications in prestigious peer-reviewed journals, Professor Gambassi is one of the leading researchers in the field of non-equilibrium physics. And so we are lucky to have the possibility to listen today to his dissertation. The title of the talk is Centenarian but Still Surprising, the Ising Model and its Dynamics. And with this, I leave the word to Professor Gambassi. Thank you.
So first of all, I would like to thank Professor Ambrosio for inviting me to this event in memory of Federico, with whom I share not only, as we said, the research field, but also a number of life experiences and friends. Preparing my seminar, I thought of Federico and of his inquiring mind, and therefore I chose a subject, the Ising model, which is, in spite of being almost centenarian, is still a fundamental, in theoretical physics, being a source of endless inspiration, connections, and surprises that I'm sure Federico, to whom this talk is dedicated, will enjoy. Talking about this kind of long inspiring and challenging problems, I would like first to quote what Professor De Giorgi, dear to Scuola Normale, and also particularly to the director and to many faculty of the Scuola Normale, once said that a nice problem, even if you don't solve it, keeps you company if now and then you think of it. And in a sense, the Ising model can be thought as such of this model. The Lenz Ising model was actually introduced in 1920 by Wilhelm Lenz, and it was solved by his PhD student Ising almost 100 years ago. Ernst Ising was born in Cologne, that's a link with Germany. He studied in Göttingen, but then he had to flee Nazi Germany to the US, where he became an elementary school, a school teacher, and seemingly was not even aware of the success that this model was having in science. And so the problem that the model was trying to address was at that time they were studying the magnetic properties of material. And so the idea was to try to see whether it was possible with a model to reproduce the behavior that of the magnetization that some metallic materials develops when they are subject to an external magnetic field. So, because what was surprising is that at a certain temperature, the magnetization was responding somewhat proportional to the applied field, but upon decreasing the temperature, a dramatic change in the behavior of the system was observed, showing hysteresis and, most importantly, or even the spontaneous magnetization, that is, the system was magnetized even in the absence of the field. And this is what keeps the compass pointing towards the north and the magnets are attached to our fridge, spontaneous magnetization. So, and then they thought to introduce a simple model in which which consisted of a sequence of elementary magnets pointing up or down associated, which was a real variable plus or minus 1, so that the configuration of this elementary magnet called spins was simply a sequence of numbers plus or minus 1. To these numbers, there is associated an energy in which there is a coupling with J, taken positive, which favors the alignment of which spin, which is with its two neighbors, and this is a term which favors order. And then in the presence of a magnetic field, also a term which tends to favor the alignment of the spins with the external field. Now, having this model, one can study the statistical physics of this system, that is this fully encoded in the Boltzmann probability distribution for a certain configuration when the system is equilibrium at a certain temperature T. And so once you have this probability distribution, one can calculate the value of the magnetization that is the average of the spin as a function of the external field and temperature, just to discover that unfortunately with this model, the magnetization was always vanishing. So the model was always in what is called the paramagnetic phase. So this seemed to be a failure. But we defined the model in 1D. The model was originally defined in 1D, but can be really immediately extended to the case in two spatial dimensions on a square lattice, in which the interaction, each spin interacts with its four neighbors, the neighbors on the lattice. Okay. So if you do this extension, the Hamiltonian is the same, just the sum is extended to the four neighbors instead of the two neighbors. If you do this extension, then in 1944, Larsson-Sager showed exactly, with an exact solution, that the model, in the absence of an external field, indeed can account for the fact that there is a transition from the ferromagnetic to the paramagnetic phase, in the sense that the spontaneous magnetization of the model gradually vanishes upon approaching what was known at the time as the Curie point, just to become paramagnetic. This point is now called the critical point. Is this an accident of 2D? No, this was due to the genius of Lev Landau, who in 1937 showed that in a sufficiently high dimension, you reproduce this phenomenon. So this is something which happens above 2 dimensions. And this impact of this model and its solution on the conceptual foundations of statistical and theoretical physics is actually difficult to summarize in a few words, because here I just listed some keywords, but essentially this model provided the basis for a number of further developments and advances in the past 70 years. So it is still a source of inspiration and motivation, and also establishing links with other fields of physics and mathematics, and not only combinatorics. Nonetheless, up to today, there is no solution, no exact solution, probably it's even unclear whether there can be, of the model in 3 spatial dimensions, which is the generalization of the 1 in 2 dimension. It was about equilibrium behavior. On the other hand, dynamics is also very interesting. Beyond the equilibrium property, so we have to keep in mind that the classical thermal noise, at which the system is subject, tends naturally to flip the spins, and particularly those whose flipping decreases the energy of the system. Okay? So in order to understand which flips decreases the energy of the system, let's consider one spin, for example, pointing up, and the configuration of its neighbors. Let me assume that there is now no external field. So now if we have this configuration, the thermal noise flips these spins, the consequence is that it will create 4 domain walls marked here in red. The domain wall being defined as the line which separates spins with opposite orientation. And if we look at the Hamiltonian, building a domain wall costs an energy 2J. So the total cost of doing this move then is 8J, okay? So while instead, if in the initial state there was already 1 domain wall, by flipping this spin, one will create 3 domain walls. So with a net of the creation of 2 domain walls, which also costs lots of energy. While if instead the initial state there are two domain walls, like here, and one flips this spin, then the number of domain walls is the same. So there is essentially no variation in the energy of the system. And the same is true if the two initial domain walls have this different distribution. And so after the flip, they will simply displace. Okay? Now, if instead in the initial state there are 3 or even 4 domain walls, after the flipping of the spin, their number decreases. So that's clearly a move which is energetically favorable because, as I said, stochastic noise tends to decrease the energy of the system. Okay. While if we now add also the external field, as I said, has the tendency of trying to make the spin aligned with its direction. So there will be an energy cost for flipping a spin which is correctly aligned towards one which is oppositely aligned, while there is a gain on energy if the flip occurs in the opposite direction. Okay? So now, with this in mind, we can look now at what happens at very low temperature. So we take the model at very low temperature, much smaller than the coupling J. So that essentially, because of this constraint, the system will undergo random flips in which the flips which increase the energy are heavily suppressed. So essentially, the possible flips will be only those which have a variation of the energy smaller than 0. That, based on what I said before, means that in the initial state, there are at least 2 domain walls. Okay? So now imagine we would like to understand what happens if we take a large system of spin up, replace the depicted here, and we produce an internal domain square, just for simplicity, the very famous square cows that are very dear to physicists. So, and then we focus on what happens at the coordinate. So essentially, let's focus on a configuration which we think to be infinitely extended in this direction, in which there are spin up outside and spin down inside the coordinate, okay? So now this means that there is a domain wall which has this straight line with the coordinate. As I said, the stochastic dynamics will allow only flips of spins which have at least 2 domain walls. And then if you go by inspection, you expect all these spins. The only one which has 2 domain walls is this one, which has a flip, in a sense, for free, because flipping it costs no energy. So this means that the system will fluctuate between this configuration, and then randomly this spin will be flipped, and then maybe it can be flipped back, going back to this configuration. Or otherwise, from this configuration now, there are 1 and 2 spins possible with 2 domain walls in its neighbors, and so one of these might flip, or maybe the other might flip, or flip in one direction, flip back, going back to this. And so if you keep on constructing it, you will see that after a certain number of random flips in one direction or another, this domain wall or string will take a certain shape. Okay? And actually, if you check, because of the initial state we choose, there are essentially no spins which have more than 2 domain walls. And also dynamically, there can never be spins with more than 2 domain walls. So essentially, the only moves that they are all at 0 energy, because those with more than 2 domain walls which lead to negative energy, so a loss of energy, are not geometrically present in the model. This is an important point which we turn out later. Now, if we add an external field will try to make more probable the flips of the spins towards in the direction to make the flips towards the final state being in the direction of the magnetic field. So, for example, in this case, we will try, if the field points up, we'll try. It is more likely that the spin flips up than down. So there will be a bias in the kind of transition between the states. Now, so the system, you prepare the system, you let it evolve under the random noise, and then after a while, you will find something like this, okay? If you find that you look from far, you can see that, in a sense, the system, this domain wall will attain an average shape, depicted here, with some fluctuations, and this average shape has departed from the original profile depicted here by a typical length scale that I call L of t. And now this length scale is very interesting because in the absence of the field for h equal to 0, which means that the transition between the states are all equally probable, then the system does, the interface does a sort of random walk, and so it has a diffusive behavior. While if the field is positive, so this boundary, this corner tends to be eroded, favoring the advancement of the external part towards the inside, and indeed this L of t grows linearly in time, so this is the ballistic behavior. While if h is negative, it's easy to realize that the moves that can do much and the system will be sort of blocked to the initial configuration. Okay? So this is about what happens in the classical case. Now the model can go quantum. So we go towards the quantum Ising model, in which a classical variable which was plus or minus 1 at each side of this one-dimensional lattice or two-dimensional lattice, because the generalization is simple, now becomes a superposition. Sorry. I think I understood now. Just I apologize. I have a okay. So, can you hear me?
Yes, we can hear you.
I could not. Okay. Okay. So at each site, what was the classic variable becomes now a quantum superposition of the two possible states, which are the eigenstate with possible different eigenvalue of the so-called spin operator sigma z. And this coefficient here, their modulus square, is actually the probability that a measurement on the system, you will find it in the spin pointing up or pointing down. Okay. So if one introduces this representation of this operator, which is a 2x2 matrix, this representation here, then the spin actually becomes a vector with two complex components. And it's also important to introduce the operator sigma z, whose action on the basis of the operator sigma z, the eigenvector of the operator sigma z, is just to flip it. So in a sense, the operator sigma z tries to do what the noise, the thermal noise, does in classical system, this flipping. Okay? Now, the Miltonian of the quantum Ising model is this one, which, if it were not for this term, so forget about this term here, this part here then would involve only the operator sigma z, and the operator sigma z can be diagonalized in the basis of its eigenvector. So once you take as a basis of your Hilbert space the vectors which are the eigenvector of sigma z, this part here will just resemble the classical one, because each sigma will simply take the plus or minus value as in the classical var. So without this term here, this is essentially a classical model. So is G what makes the problem quantum, as I said, because it plays the role, looks like that's what the temperature does in classical system, it tries to flip this. So in spite of this quantumness, actually, there is a very interesting result. So one first important connection, one of these interesting connections which emerge in physics. If we would like to study the equilibrium behavior of this quantum system, what is interesting is that, imagine we take this model in these spatial dimensions, so this sum is extended to the nearest neighbor in this spatial dimension. So we take this system, quantum, in this spatial dimension, and we study its equilibrium property as a temperature which I indicate as beta to -1. It turns out that its partition function is exactly the same as that of the D plus 1 classical model, in which which has in the additional spatial dimension, it has a finite extent given by beta. So it's like a film of an Ising. So you take a d-dimensional quantum Ising model, you get a d plus 1 dimensional film of the classical model, in which the temperature of this classical model is simply proportional to G, because as I said, the G acts as a sort of temperature for our model. Okay? So in a sense, the equilibrium properties are sort of trivial. Quantum and classical are clearly connected. But what about dynamics, and especially non-equilibrium dynamics, which as we heard, where, I mean, as we know, where it was the interest also of what Federico was studying during his PhD. So let's take the two-dimensional quantumism model, which give us company for the rest of the talk. So we said that equilibrium, it is exactly essentially the same as the classical ism model in a film. And so its phase diagram, we can copy it from what we know from classical physics. And this, in particular, if we are at zero temperature, if we are interested in behavior at zero temperature, this is indeed the three-dimensional ism model, because the film has an infinite extent in one direction, so you have really a complete new direction. And this model is known, as I said at the very beginning, although we don't have the exact solution, to undergo a ferromagnetic to paramagnetic transition to a value of the critical coupling G, which is proportional to J. If instead, and so this is the quantum critical point belonging to the 3D classical universality class. If instead we study this model at finite temperature, then this critical line extends into a critical line. And the behavior here is the one of the two-dimensional classical ism model. So the phase transition is there, but given that now we are going to study the dynamics in the low temperature regime, we will essentially consider like J being infinite. So these phase transitions, they become irrelevant, and we will be sitting deeply in the ferromagnetic phase. Okay? Now, if we assume that this coupling J is much larger than the HG, as I said, there is no phase transition. We are deeply in the ferromagnetic phase, but the dynamics is non-trivial. We can study then the dynamics in the basis of the eigenvectors of the sigma Z operator. And the model, essentially, this sigma Z becomes essentially the classical case. And the model, so remember that in this approximation, these terms essentially do not count. The model looks like the classical ism model. And therefore, if we want now to inspect the dynamical moves, which are the energy cost of the dynamical moves, which are these flips induced by the coupling G, we can simply go back to our to the analysis we did before of the classical case. And what we discovered, so this is the table of possible moves with the change in Hamiltonian. Remember that in this approximation, the model is primarily isotoplastic. Now, in this case here, I mean, these moves here and these moves here are not allowed because they will violate conservation of energy and will take your model off resonance. Because remember now in the quantum dynamics, energy has to be conserved. So this will give you two behavior which are off resonance, while the only possible moves which remains are those in which essentially the domain walls are displaced and moved, but no domain walls are created. And then also the reverse transitions are allowed. Okay? So the dynamics is then essentially, it is effectively given by this effective Hamiltonian here, in which simply moves the boundary. And the other important thing is isoperimetric dynamics, in the sense that the length of the domain wall is unchanged because you simply displace it, but without changing its length. Okay? This means that if you start with an initial state, which has a domain wall of length L, the quantum superposition induced by the dynamic of this evolution will simply be a quantum superposition of states with the same domain length. Okay? In spite of the fact that this Hamiltonian now is simplified and we casted the problem in a simple case of moving boundaries, now the dynamics can be still very, very complicated. For example, if we start from a domain like this Hamiltonian here can lead to the complete fragmentation, like here, which is isoperimetric, of the initial domain. Okay, so this is a complete domain, disappears and is eroded. Even if you focus on the cases which you have separated strings or domain walls like here, these domain walls can actually merge. For example, by flipping this pin here, you go from here to this, and then they can merge. Or they can even branch. So if you have a domain wall like this, by flipping one of these two, you can create an island. So the dynamics is still very, very complicated. So the strings move, recombine, and branch. So the question is, can we simplify all this? The simplification comes if indeed we start from an initial state which is like a corner, like in the classical case. Indeed, if we take a corner like this, or actually this can be generalized to any Lipschitz continuous function, we can, essentially what we can do is exactly the kind of reasoning that we said, because the moves are exactly the same as in the classical case. So we can, the only configuration which are resonant with the initial configuration are those which are obtained by flipping the spins which have exactly two domain walls around it, okay? So and then you flip and then you will end up with a certain shape like this, okay? What is interesting, and now this is another interesting connection, is that the shape of the eroded part takes the form of what is called the Young diagrams, which are familiar to those who study mathematicians, especially those who study the representation of groups, of the symmetric group in particular. So there is a one-to-one connection to Young diagrams. And as it was the case also in the classical case, by inspection, you will realize that this part here of the Hamiltonian, which is responsible, as I said, for the breaking and the merging of domain walls, is not effective. So in this subspace of Young diagrams, this part here is not effective, so can be excluded from the Hamiltonian. So this means that if you put an original string, being Lipschitz continuous, or like this, it will move, but it will not break. And this is a considerable simplification. Okay? So now there is still another interesting thing that I'm going to point out. So we have sort of reduced the problem of studying the dynamics of a complicated model in the bulk to what happens at its boundary. And actually we can go from quantumizing in 2 dimensions to a system of fermions in 1 dimension, okay? So in a sense, we will go from this 2-dimensional case to fermions in 1 dimension, which is another interesting and simple example of what is very fashionable now in string theory and quantum gravity, that is a simple case of holography. So I have a 1-dimensional model which is able to contain all the information I need about a 2-dimensional model in a 1-to-1 correspondence. How do we see that we can do this mapping? Well, let's go back to our domain which has been eroded. So let's forget about what is outside the corner. Now we have, we want to describe this interface. Remember, this is a quantum state. So how can we describe it? Well, if you rotate it and you project vertically, what you can do, you can project the segments which make the domain walls, the boundaries of the cells, and you go along the domain wall, and you will assign an empty site whenever this goes down, and a site with 1 quantum fermion whenever you go up. Okay? So essentially, from a configuration of this domain wall, you can construct, you can associate the configuration of a system of quantum fermions on a line. Okay? So it means that when it goes down, you associate the vacuum state of the quantum chain, or you create one single particle. It means there is a fermion in that case. Okay? So then we are projecting the dynamics of the interface into the dynamics of a fermions 1-dimensional lattice. And this is 1-to-1 correspondence, because once I know the density of fermions, I can reconstruct the shape of this class, of this interface, by simply counting the number of fermions which are to the left of a certain point. So it's a simple correspondence. So now we have essentially saying that the Young diagrams are in a 1-to-1 correspondence with the state of fermions in 1D, which is something which was investigated also 20 years ago by Okun. What is interesting then, we can write the Hamiltonian, which fuels the dynamics of these fermions in 1D, and therefore induced by the one of the interface. And it turns out that this Hamiltonian, which I report here, is the one of 3 fermions hopping on the lattice, plus an external linear field, which is known to undergo the so-called Wannier-Stark localization. I'm about to conclude. So what is interesting is that, you remember I introduced at the very beginning for the classical case this typical length L of t. I can also introduce it here. So this length of t, the problem can be solved for a generic initial condition, especially for the corner. If you do it for the corner, you discover that there is a length L of t emerging, in terms of which the average shape, remember that these interfaces are quantum fluctuating, so it makes sense only to talk about average shape. The average shape takes a scaling form of this length L of t, and the scaling form, the scaling function here, is actually what was found by Okunkov by studying the measure concentration phenomenal of the Plancherel measure in representation T. So a completely mathematical.
Vedi un po', sto in modalità solo audio.
Qualcuno ha l'audio aperto. So, and now just to give you an example, let's look at the dynamics. So this is our original corner, tilted. And now what is the dynamics of the average quantum interface? You will see that it goes back and forth. Back and forth. So it oscillates, which is a complete at variance with the classical case. Remember, in the classical case, the bubble was eventually eroded. Okay? So there is essentially no melting of the corner for h different from 0. The corner is not eroded. Now, it's then interesting to compare what we have learned about this typical length L of t, which is, if you want, the penetration of the erosion, this object here, as a function of time. So what we learn is that for the quantum case with non-zero magnetic field, we look at this formula, it is just periodic, so it oscillates like this. When you take the limit h going to 0, so the flips are not biased, then you discover that it tends, it becomes the linear approximation of this. So then the corner is eroded ballistically, still with the same scaling function as this one. Now, if you remember instead the classical case for h equal to 0, the L of t was growing diffusively as the square root of t, while for h larger than 0 was ballistic. And for h smaller than 0, it was staying constant. So what we learn here that there is a distinct, markedly different from equilibrium behavior in the classical and quantum case. And there are clearly related to this conclusion, there are some challenges related. For example, how comes that the bubble does not melt in the quantum case? Because the quantum case, you would have expected that the bubble is energetically costly, so it should, expecting some sort of thermalization, erode. Okay? So this was just to give you some a feeling of the breadth with which Federico was nurturing himself during his PhD. I mean, he was doing research on different teams, but it was like the alphabet of what he's doing. And I think for the manifold connection that I briefly mentioned, he really would have enjoyed this kind of problem. So let me conclude. So my conclusion, I mean, I apologize I didn't quote the literature and all the information, you can find it in this recent article. So the conclusion is that the classicalism model is a centenarian, simple, nice model, but it's surprising with lots of inspiring connections. This kind of connection that Federico liked a lot to create. As I said, that there is this kind of result is a challenge for the expected thermalization. And then clearly we are currently working, understanding what happens if you have generic boundaries and what happens in higher dimension. Okay. With this, I would like to thank you. And I apologize if I've been too technical, but I think that by showing you lots of pictures, I also showed you how physicists think, which is a connection to art. So there is an artistic link in the scientific way of thinking. And then I thank you very much.
Thank you, Professor Gambassi, for the nice talk. I think we have time for a short question, maybe, if someone has one. And I have a question from the chat, from Paolo, that is more on a divulgative aspect, let's say. What makes the Ising model so universal that can be crucial for the understanding of models that are so different, or frameworks that are so different from, for instance, magnetization, critical phenomena, and dynamics of complex systems, like, for instance, the motions of birds in sky, and also computation?
Okay, so that's an interesting question. So, very nice question. So let me phrase it like this. The easy model was one of the first examples in which one could prove rigorously that when you have small, many degrees of freedom, remember these elementary magnets, which taken separately would have a quite miserable and boring life, when you put interaction, when you make them interact, for the fact that there are many of them, you can develop completely different collective behaviors. So the key word now is collective behavior. So the easy model was one of the first examples in which you could prove the emergence of collective behavior, which, as I said, also the development of magnetization is a collective behavior. So the same boring system at different temperatures can have a completely different collective behavior. So this happens for the starlings in the sky. So starlings, which are the subject also of this nice recent book by our Nobel Prize Sergio Parisi, they show clearly a collective behavior. So the task of a physicist, a statistical physicist, is to understand what determines this collective behavior. There is clearly no intelligent director for this motion. This is something which results from simple, not particularly clever birds. Okay, and this is the same. And this is the task of statistical physics. Then clearly, when you have collective motions, typically you develop a behavior on a scale which is much larger than the individual scale. And this is actually what is the root of the concept of universality in critical phenomena, which means that systems which are microscopically different, they might nonetheless develop a similar collective behavior at a much larger scale. And this has connection then with field theory and with what is called then statistical field theory and many other this idea branches out of essentially in all corners of theoretical physics.
Thank you very much. I think we have another question, a bit more technical, so from Giuliano. What are the updates on the solution of the three-dimensional Ising model?
Okay. So, as far as I remember, nothing spectacular. In the sense, when I was still a student, actually a PhD student at the Scuola Normale, so perfezionando, there was a period, so I'm talking about the beginning of this century. At the beginning of this century, there was there were days of very strong excitement because people, they were thinking that there was a way of making an exact solution for the three-dimensional Ising model. But then there were even partial results showing that there cannot be an exact solution of the Ising model. So I think few people are still looking to an exact solution because we have anyhow many other methods and approaches, less analytical but more, for example, numerical or based on this idea of field theories to understand what are the collective properties of the three-dimensional Ising model, which are perfectly known. I mean, if you ask me how to characterize the critical behavior of the three-dimensional Ising model, everything is known nowadays. I cannot solve it exactly, but I know everything. And which for a physicist is more than enough. I know mathematicians have a different perspective, but for theoretical physicists it's perfectly fine.
Okay, thank you very much again, Professor Gambassi. And this was the last speaker of this first part of of the Federico Tonielli Award. And so we are almost at the conclusion of the first session. But before, I would like to invite again on stage Piero Viti and Mauro Bibbò for another musical contribution. This time they have prepared for us an homage to Tuscany, and so also to the place that is hosting us today. And the music has been composed by the Tuscan musician Mario Castelnuovo Tedesco. So I leave the stage again to Piero Viti and Mauro Bibbò with Tempo di Siciliana by Mario Castelnuovo Tedesco. Thank you. Thank you again to Maestro Viti and Maestro Bibbo. And with this, we conclude the first part, the first session of this workshop. And we have almost 20 minutes for a coffee break. And then at 11, we will be here again to connect with Köln for the second session, organized by Professor Sebastian Diel. And so thank you, everybody, and see you at 11.
Yeah, so welcome everyone to the Cologne part of the Federico Tonielli Award 2022. So I welcome everyone in Cologne who's come here personally, and also everyone in Pisa joining to the other part of the event being held in Italy. Yeah, we hold this award ceremony in memory and honor of Federico Tonielli, who was a colleague and friend of us here in Cologne as well. He was a PhD student, and I was a colleague of him. My name is Thomas Müller. And yeah, we give a prize away in his honor. Yeah, Federico passed away very tragically and suddenly 2 years ago in June 2020. Yeah, as I said, the award consists of an Italian and a German part, and the Italian part of the ceremony has already started before. In Pisa, and where Federico did his studies before he moved to Cologne. Yeah, again, a very warm welcome to all of them in Pisa. During this award ceremony, we will have different speeches, among them from Federico's family, and we will hear in the Cologne part music played by Malina Mancheva, who's playing the violin, and Vanya Tantikova, who's playing the viola. And yeah, to start things off, I would like to give the word to Professor Paul van Lostrecht, who is the Dean of the Faculty of Mathematics and Natural Sciences at the University of Cologne, for some welcoming words.
Good morning, everybody. It's dear family, first of all, dear colleagues, dear students, dear friends. It's an unusual day today because of Pfingsten, one Pentecost, and I'm actually really happy to see that many of you still came on this Saturday morning, because the award today we are giving to a talent is really an important thing. It's about rewarding people who are really good and with that actually promoting, let's say, the international collaboration in science and between people, and I think that is a no-brainer that's really important nowadays. As the Dean of the Faculty of Mathematical and Natural Science, I would, as I said, I would like to warmly welcome you at this occasion celebrating young talent at the Federico Tonielli Award Ceremony 2022. And let me, for those who don't know, start with a few words about our faculty. I think most people here might know, but for the Italian side, maybe a little bit. Our faculty has been founded in 1955, and it really ranks among the biggest faculties of mathematics and natural sciences in Germany. It's very internationally oriented. We have a large number of staff and students from all over the world. And to give you an idea of the size, the faculty has about 9,000 students, 180 professors, and a multitude of other people, making our faculty a living organism, so to say, and a successful organism. We have 6 departments: biology, physics, mathematics, and computer science, chemistry, teacher education, and geosciences. And of course, excellence in teaching and research are the key values of our faculty. And one of the most important ingredients to achieve this excellence are the young creative members of our community. And apart from the 9,000 bachelor master students, we have about 1,000 doctoral students, of which, obviously, if you calculate, about 200 per year graduate. And also there we are very internationally oriented, and Federico was obviously one of those international exponents in our faculty. And in these many promising and excellent doctoral students, Federico Tonielli, as a PhD student, has been really an outstanding example of the promise and the excellence. He was highly creative and successful in his research, very open, internationally oriented, I repeat, internationally, and an example for many of his colleagues. And the prizes bearing his name, award today, are not only in the recognition of excellent young talents both from Italy and Germany, but also continuation of the exceptional engagement and spirit of Federico. I am, as I hope you all are, looking forward to an enjoyable award ceremony, which presents an interesting blend of beautiful music. I know at least the titles I've seen, so yes, intriguing science and excellent young researchers. At the end, I really want to thank a few people, and this is in particular the family, but also Sebastian Diel, for actually pushing this, to make this an event, to install this Tonielli Award. And I think we should all be very grateful for their efforts, and I hope it's a continuing effort for the next, whatever, decades. And with that, I would like to finish and just wish you an enjoyable morning and ceremony. Thank you.
Yeah, thank you very much. So next we will have our first music part, which will be Invention 1 by Johann Sebastian Bach, played by Balina Vancheva and Sonia Tantikova. And yeah, as we've seen in Italy, they have chosen the same composer, so maybe it's a good idea to play Bach, and especially because of the connections that he has to mathematics, as I'm told. So we're looking forward to the first music part. Yeah. Yeah, thank you very much. Next point is, next we will give our attention to Italy, to Pisa, where we hear some words by Professor Gianfranco Buffardi. He is the president of the Institute of Human and Existential Sciences in Naples, and he's the uncle of Federico. And together with the family, he is the initiator of the Italian part of the prize. So I would like to give the word to him.
Dear friend, I have so much people to thank. so I apologize myself, but I wrote all, so I wouldn't risk forgetting anyone. This second edition of the Federico Tonielli Award could not have a better location than the two prestigious universities, the Scuola Normale, Superiore of Pisa, from where I am speaking now, and the University of Cologne, connected with us for the ceremony. As president of the Istituto di Scienze Umane Esistenziali, proposer of the award by the request of Federico's family, I must thank the two universities and obviously their chairs, Professor Luigi Ambrosio and Professor Paolo von Losrecht, as well as all their collaborators who have worked hard to make it happen, and especially, particularly Elisa, Mariella, Vasco, and Thomas. I have to thank also the members of the scientific boards who awarded the two scholarships. From Germany, University of Cologne, Professor Alga Zuccaro, Vice Dean for Research, and Professor Ines Neundorf, Vice Dean for Equality, Diversity and the Promotion of Young Scientists. From Italy, Professor Michele Benzi, Numerical Analysis from Scuola Normale of Pisa, Professor Alessandro Ottaviani, Science History, University of Cagliari, and my dear friend and big supporter of the Istituto di Scienze Umane Esistenziali, Professor Oreste Trabucco, Modern Philosophy, University of Bergamo. With him, I thanks very much my very old friend and director of the Istituto, Fernando Boscaino, constant help in my engagement with the Institute. I particularly thank all the young PhD students, very numerous this year, that participated as candidates for the award. I believe all of us to thank the master Spiro Viti and Mauro Bibbo with their valuable interpretation, and Malina Mancheva and Vania Tantikova, I hope that pronunciation is correct, that accompanied very sweetly us in the ceremony. Federico's families and I are grateful to the principal Adriana Mincione for her initiative, which we hope that will be soon realized. And obviously, I thank all of you who are following us now with very big and sincere affection. And last but not least, I hope that he hear me, allow me a special thanks to Professor Sebastian Diel, who strongly wanted the realization of this award, involving his collaborators and constantly organizing himself with us, and mostly patiently enduring my very bad English. So I hand over to Professor Daniela Roberti, Federico's mother. Thank you.
Welcome to everybody. I think everything has already been said, but let me give my special thanks to Professor Ambrosio and to this real army of friends of Federico who wanted to remind him in this book and wanted Pisa to host the award ceremony this year in the place where all the scientific story of Federico began. And also thanks to Sebastian Diel, who was the first to want Federico to remain impressed in the scientific life of the University of Cologne with a memorial held in the University of Cologne 20 days after his death, closed in this booklet with all the thoughts of his friends. and also with this award. And it is also in Cologne that Federico surrounded himself with other fantastic friends, including those of the theater, the Ithaca Theater, and Diana is here with us today. We in the last weeks planted a tree in the center of the city with a plaque in memory of him. And this ceremony, this event, which a colleague of mine confused with a music festival, contains the true essence of Federico: science, physics, but also philosophy and art. We should have included also cooking, but it would have been a little bit difficult. He was an enthusiastic of life in all its aspects, a curious boy. I teased him saying that from being a physicist, he would have become a cold rational. But instead he was passionate about everything. And still and always, his memory intersects with music. And with all respect to all the musicians who are giving us these splendid moments of arts, a special thanks goes to Piero, the beloved uncle of Federico. Federico loved it too much. And with Piero, he often discussed and he was fascinated by the deep interaction between mathematics and music. And Federico used to say about himself, "I am ironic. I thirst for knowledge. I love politics." This is what he wrote about himself in this little book, in which I enclosed his thoughts. He continues, "I like to write, to read myself aloud and understand myself. I like to reread myself and remember myself, having photos fixed in me to be offered as a gift." And this is what he often did with his writings. He wrote a lot, and he won a prize, an award, when he was only 17 in the high school. And I believe that his soul is contained in these few lines from a poem in this book, The Future Waves. And even if it won't be forever, if now it will be to separate from a single state, from a single street into several streets, if you believe that you have lost half of yourself, don't cry. The vacuum is only appearing, is a state of motion. The missing mass is energy. Become matter again, the cycle will renew itself. So, although it is incredible and acceptable to me his loss, these hours, your love, his friends, are the energy that replaces the missing mass to me. And I hope that these two future researchers who will receive the award, I hope they will always have the right energy for the success of their research and never give up like Federico did. Thank you to all of you. Ad Maiora, to that two guys.
thank you very much for these very moving words and personal that you shared your personal thoughts about Federico with us, and it was very moving. Next up, we will have our next musical part by Wolfgang Amadeus Mozart, duos KV 423 Allegro by Wolfgang Amadeus Mozart. Please. Thank you very much. Next, we will come to the Cologne part of the prize, which will be awarded by Professor Sebastian Dier, who was the PhD advisor of Federico when he was in Cologne, and he's also the initiator of the Cologne part of the prize. So.
Thank you, and good morning to everyone. I'm very happy to introduce the winner of the Federico Tonielli Award 2022. And before doing so, let me also thank very briefly the parties that make possible this prize, represented by Professor Ambrosio, Professor Buffadi, and Professor von Lostrecht, but also the parties that make it really work. So the teams that are organizing it, represented by Elisa Guidi and Mariela Boevska. So the prize in Cologne is generally to be awarded to a young, promising researcher in the natural sciences and mathematics. And this year we had really excellent applications from mathematics, biology, and physics. And out of these, the jury selected the one of a young mathematician working on a topic closely related to physics, Ms. Céline Carriou. So she is currently a first-year PhD student in the group of Professor Peter Mörters at the Math Department. She has actually German-Canadian roots, growing up in Munich and doing her studies and graduating at McGill University in Canada. So she came to Cologne, back to Germany then, with a prestigious Canadian fellowship, plus an already impressive number of academic distinctions already at her early stage of career. So I will touch on the topic of her PhD work only very briefly. It is located in the area of probability theory and specifically deals with so-called condensation phenomena. So these are essentially, colloquially speaking, winner-takes-it-all phenomena, where specific states in a big possible state space are really overproportionally occupied and in a way that even scales with the number of available system constituents. Yeah? So this is a phenomenon that is ubiquitous and really fundamental in many branches of physics, and Ms. Carriou is concerned with analyzing, formalizing and analyzing such problems in a mathematically rigorous way. However, this is not the only topic that Ms. Carriou has been working on. In fact, both her bachelor and her master thesis already led to distinct publications. Also, these topics are closely related to physics, and her first publication actually caught my special attention due to its amazing title. It's called Hipster Random Walks. This is a phenomenon that I would have rather associated to the late time or the late night dynamics somewhere in Cologne-Ehrenfeld. But in fact, Ms. Carriou demonstrates a connection of these very special random processes to the physics of convection diffusion dynamics. So this work is published in a highly renowned mathematical journal, and Professor Mörters qualifies these as very substantial results underpinning Ms. Carriou's mathematical talent, and which concerns both technical strength and originality. So the jury was actually really impressed by this extremely strong publication activity already at an early stage of scientific career. On a personal level, as visible from Ms. Caillou's international CV, she shares with Federico the passion for exploring life and science abroad. And she's also a big fan of traveling in Italy, although so far, as I understand, specializing in the northern regions like Piedmont and South Tyrol. So as she writes in her proposal, she would like to continue along the international path and use the Federico Tonielli Award to visit 2 summer schools, one in fact in Italy and the other one in the Netherlands. So the jury is actually convinced that this is really an excellent investment of the prize money, since already visiting her very first summer school some 2 years ago, or a few years ago, gave her the tools and the inspiration to tackle her master project, which already, as we heard, resulted in a publication. So with this, Ms. Caillou, I wish you all the best and a lot of success with this plan, and that it may support you on your initial steps for the academic path that you started to travel. I would like to express my wholehearted congratulations for winning the 2nd Federico Tonielli Award. And now I'm looking forward to your presentation on your PhD project. So I would say the stage is yours.
Thank you very much. So before starting my presentation, I'd like to thank the family of Federico Tonielli and also the organizers of this event, and for making it possible for me to attend these summer schools. I'm very grateful for this opportunity. Okay, so I'll briefly present my PhD project, which is condensation in random graphs, and this is joint work with, or I'm supervised by Professor Merkus, as Mr. Thiel just stated. Okay, so let's begin with, sorry, do you know how can I remove this? Okay. Do you know how I can remove the bar? Okay. I can move it out. Okay. All right. So what is condensation? So you've probably all seen condensation already. When after showering, for example, you can see droplets form on the mirror. And so condensation, it's this phenomenon. As temperature decreases in a gas, you have drops of liquid that form. And so these drops are characterized by a higher particle density than elsewhere in the gas. And so the question is, how can we model such a condensation effect, for example? So very, very basic, simple model is the Balzan-Bins model, or Balzan-Boxes model. So imagine you have a container that's filled with gas. So gas is just consists of small particles. So here we have n particles. And then you take this container and you decide to chop it up into smaller boxes. So let's say here we split it up into 9 boxes. All right. And then now we could be interested in counting the number of particles for every box. So we say that xi is the number of particles in a box I. So for example, here x1 is 2, x2 is 3, x3 is 1, etc. And we see that there's a large number of particles in this box number 6. And so that's how we also sorry, that's how we also define condensation. So condensation is if one of these boxes, or one or several of these boxes, contains a large number of particles. All right. So I'm studying condensation in random graphs. So what's condensation in random graphs? I'll just briefly explain it. So instead of working with particles in boxes, now we can think of the boxes being nodes, points in space. And the number of particles in a box now correspond to the degree of a particle, of a point. So for example, if this point here would be our box, and we have degree, so degree is the number of edges incident to the point, which is 7 here. So then we can think of this point or this box containing 7 particles. And so my PhD thesis studies under what conditions can we observe such condensation in various different random graph models. So do we have, so under what conditions do we see some points that have a very, very high degree? So this is just the brief overview. And maybe let me just state something briefly about some applications of condensation in random graphs. So for example, we could be interested in studying social networks. So for example, I think this is the Facebook graph. So I guess every point here is a person, and you draw a link between 2 people if you're friends on Facebook. And then condensation would be, for example, here we see someone who has a lot of friends everywhere. And so it's interesting to see, okay, when does condensation occur, and when do we see condensation in such random graphs? Another example could be if we want to study the growth or the development of a city. So does the city grow uniformly around, or does the growth concentrate around certain hubs? So these are just 2 applications of many others of condensation in random graphs. Great. So thank you very much.
Document is below your computer, actually.
Ah, sorry, yeah. All right.
Yeah, actually, usually I'm not tempted to ask, are there any questions from the audience, but that's not what we're going to do today. I thank you very much for this beautiful presentation, and maybe we move over to really confer a Word document. So here you go. Okay, good. So then I hand over to Thomas.
Yeah. Congratulations also from my side, of course. Yeah. Now this was the Cologne part of the award ceremony itself. To celebrate this, we now hear the piece Huayra. It's a Bolivian folk song. I hope I pronounced it roughly correct. As we were told, this was Federico's favorite piece, our favorite song. And it was apparently a hard challenge to make it available to us now, because there's not really notes about this. We appreciate that you prepared this, and look forward to the presentation. Thank you. thanks a lot for this presentation. So this was basically the Cologne part of the award ceremony, and now we hand over again to Pisa for the Italian part of the award. So,
thank Thomas.
Yeah.
Okay, now the Istituto di Scienze Umane ed Esistenziali awarded the 2022 Federico Tonielli Award to Dr. Stefano Furlan, currently a PhD student in philosophy at the University of Geneva. His PhD thesis project, The Smile of Mnemosyne, John Wheeler from Geometric Dynamics to Quantum Information, is focused on the work of the American physicist John Archibald Wheeler, 1911, born 1911 and died 2008. A key figure in the fields of general relativity, quantum physics, and information theory, who also had a strong interest in the epistemological implication of modern physics and its relations with other sciences. The thesis project proposed by Furlan appears to be the first attempt at a comprehensive, in-depth reconstruction of the evolution of Wheeler's thought, and will greatly contribute to a needed reassessment of the influence and importance on Wheeler's ideas on contemporary sciences and epistemology. It should be noted that this dissertation requires a deep knowledge of a wide range of topics in advanced mathematics, physics, and philosophies, and that Dr. Furlan is ideally positioned to carry out this ambitious project. The award committee found the proposed research to be highly original, very well written and organized, and is most worthy of encouragement through the conferment of the Tonielli Award to Dr. Furlan. Okay, I invite Dr. Furlan to expose his project.
Hello, everyone. Can you see, can you hear me?
Yes,
Okay.
here.
Okay, so first of all, let me sincerely thank the family, the institutions, and all the people involved in this award. It is a pity that I couldn't be there in person, but nonetheless, I feel that having my name associated with it is not just an honor, but also a responsibility, and I'm truly grateful for that. I've been asked to give you a brief outline of my research, and so let me begin. John Wheeler is generally considered a towering figure of 20th century physics, but why exactly? Saying, as usually repeated, that he baptized black holes, evoked the visionary it from bit, tutored many illustrious students, and wrote a famous textbook does not sound like an entirely satisfying motivation. My dissertation, largely based on Wheeler's extremely rich and mainly unexplored archival materials, aims at providing a much more complex answer to that question, showing how and why Wheeler activities and thought shaped not only specific results in today's research, but also expectations, guiding questions, communicative styles, and so on. In order to grasp these more elusive and neglected aspects, it is unavoidable to rely on his own notebooks and working papers. According to a historical epistemological viewpoint, typical of the Max Planck Institute für Wissenschaftliche in Berlin, where I'm working, but also with the technical competence to understand suggestions or even allusions within specific issues in recent theoretical physics. Besides that, Wheeler's wide-ranging interests, inventiveness, and originality also hold some stimulating and fascinating surprises for other disciplines, including humanistic ones. My starting point, chronologically speaking, has been the beginning of the 1950s, when, from nuclear physicist Lato Sensu, Wheeler decided to dedicate himself to the dusting off of general relativity, his mentor Einstein's legacy. Thus, Wheeler became a key figure in the so-called Renaissance of general relativity, starting from around those years. That, however, was also the decade in which Einstein himself passed away in 1955. The resulting feeling of vanitas as well as a deep sense of respect towards the past, led Wheeler to help set in motion the organization of one of the last century's largest historical projects, Sources for History of Quantum Physics, then led by Thomas Kuhn and others. If this little-known active involvement of a prominent scientist is noteworthy in itself, what is truly interesting is Wheeler's relationship to the past as it emerges from his unpublished notebooks. Always passionate about history, Wheeler did not resort to it just to convey pathos or make grand prolusions, a monumental use of the past, so to speak, but also considered it a source of inspiration and ideas still waiting to have their full potential untapped, as was the case with general relativity, or to be transfigured and re-enhanced through creative analogies. This also offers the chance of closely studying an eminent case of scientific creativity and entails methodological considerations on how to properly interpret the manifold analogies Wheeler resorted to, as well as their explorative and occasionally rhetorical functions. It is not a trivial point, and it is actually crucial in order to avoid the widespread mistake of considering these analogies from a rigidly schematic and decontextualized viewpoint, resulting in a trivialization or misunderstanding of Wheeler's heuristics. Besides these, and more precisely and importantly, I had the chance to reconstruct the complex and more than decennial path that, within the context of his geometrodynamical view, but also of his military work for the Matterhorn project, led Wheeler to overcome his previous conceptual resistance against Oppenheimer and Snyder's pioneering results on the extreme phases of gravitational collapse, and brought him to accept the physical relevance of what we now call black holes. Everybody knows that Wheeler popularized the name, but it is important to realize that if he was in the position to do so, there were various reasons why he got there. Reasons perhaps not as clear-cut as a single result or a theorem bearing his name, but certainly no less important. Some attention in the reconstruction was also paid to the neglected history of the parallel developments in the Soviet Union, in particular in Zeldovich's group, with which Wheeler started to interact already during the 1960s, Cold War notwithstanding. Furthermore, following in this way the development of Wheeler's ideas, another side of his engagement with the past, or another facet of his uses of history, emerges. What Wheeler kept referring to as Einstein's vision actually was becoming more and more his own vision. Likewise, the heuristic methodology he adopted, daring conservatism, designation which also includes his political positions, to be confronted with Eisenhower's dynamic conservatism, was put under the aegis of Wheeler's other great mentor, Niels Bohr, as much as it was arguably his own creation. Clearly, this strategy was also meant to anchor Wheeler's bold speculations, especially those lacking, at least for the moment, a possibility of empirical confrontation. In this way, he started to build or suggest narratives or counter-narratives aimed at providing a sort of pedigree for his own ambitious ideas, especially those left for future developments, a practice that, more or less implicitly, survives to these days in some quantum gravity approaches, each one telling the history of recent physics in a conveniently selected way and claiming the legacy or the dream of some illustrious name. And that is why investigating the papers of a key figure in shaping expectations and research questions that are still open nowadays is not just historiography for archives. After a couple of decades working within the framework of geometrodynamics and trying to build a theory of quantum gravity, Wheeler recognized at the beginning of the 1970s that his general relativity-based program could not have the last word and that he needed some more radical ideas in order to accomplish the unification of his two mentors' legacy and build a new picture of the natural world. The variety of his references and suggestions has led interpreters either to be utterly confused or to pick just one of them, ignoring all the others. A comprehensive and diachronic perspective was thus very much needed. After this new conversion, Wheeler restarted to meditate on Bohr's lesson in quantum physics, taking into account other quantum approaches as well, and developed it in a bold and original way that brought him to touch upon cosmological, biophysical, and epistemological issues, as well as to inspire new work in quantum foundations, especially after he retired from Princeton in the mid-70s and moved to Texas. Besides many suggestions in various directions, all this led to a deep rethinking of the notion of physical law itself, and ultimately to the vision that got labeled with the famous phrase, "it from bit," information as more fundamental than things. This, nonetheless, should not be taken just as a speculative change in the basic ingredient, so to speak, of the world. The search for new ideas and structures pushed Wheeler to establish a series of extremely fascinating and almost entirely unexplored before dialogues, not only with other distinguished physicists, not often associated with him, such as the late Heisenberg, Hoyle, Caianiello, von Weizsäcker, and so on, but in a truly transdisciplinary way with scientists from other areas, Manfred Eigen, Prigogine, Delbruck, Eccles, or eminent logicians and mathematicians such as Gödel, Hao Wang, Quine, Paul Cohen, as well as philosophers, historians, and artists, since a visual component has always been crucial for Wheeler's style of practicing and communicating physics. Moreover, trying to understand in a deeper way the cultural background of those who remain these two main sources of inspiration, Einstein and Bohr, Wheeler got actively interested in the history of philosophy, which in turn prompted him to make a creative use of suggestion from figures such as Berkeley, Spinoza, Leibniz, Peirce. They became, he used to say, a sort of intracranial colleagues. The not so trivial task of reconstructing, in the light of archival material, what he actually meant by allusions that are usually neglected as some superficial name dropping, has proven particularly fruitful in the case of Wheeler's highly original engagement with Leibniz ideas. All the necessary precautions that are required for such an operation in order to avoid anti-historical superficialities and sensationalism, as unfortunately happens quite often, also offer the opportunity to make broader considerations on how to address the relation between the history of recent physics and the history of philosophy or other humanities, trying to show in a cogent and well-documented way the specific passages in which some idea could have played a role. In short, and in conclusion, I hope to have offered some suggestions on the importance of evaluating how Wheeler ideas and directions of research have shaped many expectations and questions that are still open in today's quantum gravity approaches, as well as forging a communicative and evocative style that for the last few decades has characterized, for good or bad, the popularization of the frontiers of theoretical physics. Thank you very much.
Many thanks, Stefano, for this interesting presentation. By this certificate that I ideally give you, I confer you the Italian scholarship of the Federico Tonielli Award, second edition of 2022. Thanks, and many compliments.
Thank you. Thank you.
I don't know if I should announce this, but okay, there will be another piece of music played by Piero Viti and Mauro Bibo in Pisa. Am I right? I'm sorry. Okay, yeah, thank you very much. That would have been indeed a pity to miss that. So a great finale to this award ceremony. And yeah, with that, I want to now really close the session by congratulating again the winners of the award and thanking everyone who made it possible to have the ceremony and to give away these scholarships. Thank you.